So I just want to talk about the Monty Hall problem. This is an optional video. The Monty Hall problem is a very, very famous problem in statistics, which dates to 1975. It was actually in American Statistician, the journal. And the reason why it's so famous is because it's easy to describe, it's easy to understand, and yet the result is rather counterintuitive. And so I'm just going to go through quickly. You can go online and you can find a million references, not literally perhaps, to the Monty Hall problem. You can also, there's journal articles on follow-ups to the Monty Hall problem. There are extensions to the Monty Hall problem. There's a lot here. But let me just, first of all, I'm going to tell you what it is briefly, and then I'm going to give you one explanation as to what's going on. So the Monty Hall problem states this. It says you have 3 doors, and you get to pick one door, okay? So for the sake of argument, let's suppose we pick this door to win a prize, okay? And behind 2 of the doors, we have goats in the original Monty Hall problem. And behind one door, we have a car, okay? Or you can imagine whatever you want. And suppose we want to win the car, we don't want the goats, okay? So let's suppose, for example, there's a car here and a goat here and a goat here, but we don't know that, all right? We pick one door. Then what happens is Monty Hall comes over and he opens up one of the doors that has a goat. And I'll show you in a second why we can be guaranteed that he can open up a door with a goat. Okay, so he shows you one of the wrong doors. The question is, should you then switch? He gives you the option to switch your choice or stay with the door that you've already selected, and then you'll get whatever is behind that door. And the question is, should you switch or not? What is the probability that you win the car if you switch? What is the probability that you win the car if you do not switch? That's the Monty Hall problem. Okay, so there are literally dozens of ways to approach this problem. Here's one way that I like to describe what's going on for high school students and even early university students. Okay, so I want to look at 2 different cases. We have the 3 doors. Now, first of all, let's suppose it's car, goat, goat, and you pick car. Obviously, Monty has a door with a goat to choose and open up. If it was car, goat, goat, and you choose this one, Monty will open up this door to show you a goat. And if you choose the last one, Monty will open up this door to show you a goat. Okay, so no matter what you choose, Monty Hall will be able to open up one door with a goat. All right, so that's out of the way. Now, I'm going to use a probability tree. If you're not familiar with probability trees, then this may not clear anything up for you, but this is the approach I'm going to use. It's a common technique that we will actually discuss later on in this course. So here we are. There are 2 things that may have happened once we make our initial selection. Either we selected a car or we selected a goat, and we obviously don't know what the reality is. If we selected a car, the chance of that happening is 1 out of 3. Okay, and the probability that we select a goat is 2 out of 3. It's more likely that we select a goat because there's more goats than there are cars. There's 2 goats, 1 car. Okay. Now, let's follow through what happens. Let's suppose that we switch. Okay, that's the first case. And then secondly, I'll go through what happens if we don't switch. If we select the car, Monty shows us one of these, and then we switch, we are guaranteed to get a goat. It's 100% guaranteed. Okay, I could put a 1 there because on these, you'd normally go 1/3 times 1, but we're guaranteed to get a goat if we started with a car. And vice versa, on the other hand, if we have a goat and then he opens up this door and we switch, we're guaranteed to get the car. Either it's because we took this middle one and he eliminates the last one for us, or it's because we choose the last one, which is a goat, and he eliminates this one. We get a car, right? Notice in this, Monty Hall is getting rid of the other bad outcome. That's part of the key to this. So if we choose a goat to start with and we switch, then we're guaranteed to get a car. Okay, so you can see right here that by switching, we have a 2/3 chance of getting a car. And the reason is because we have a 2/3 chance of starting off with a goat. And by the structure of the problem where Monty Hall opens up and therefore eliminates one of the bad possibilities for us, we're guaranteed to get a car if we got a goat the first time. And there's a higher probability of getting a goat the first time than there is getting a car, so we actually have a better outcome here, a better chance of getting the car. Let's run through and just see what happens if we keep our original choice. Again, your original choice, you have a 1/3 chance of getting a car and a 2/3 chance of getting a goat. And now, what happens? Let's get the 3 doors down here. Let's suppose it's car, goat, goat, and of course we don't know that. We choose this door here. We got a car, and then Monty opens up one door with a goat. So we know this isn't the one, but we do not switch. We stay with what we have. Well, then we're guaranteed to get a car. In fact, if we keep our choice, we're guaranteed to get whatever we chose originally. So if we got a goat and we don't switch, right, we're guaranteed to get a goat. So if we chose this one here, for example, it's a goat, or equivalently the last one, and Monty shows us the other one, and it's a goat, we eliminate that, but we don't switch, we still get the goat. Okay, so here you can see the chance of getting a car is 1 in 3, the chance of getting a goat is 2 in 3. Okay, so keeping the choice, we have a 1/3 chance of having the car. Switching, we have a 2/3 chance of getting a car, so switching is obviously better. Why? Because we're more likely to have the wrong outcome to start with. We're more likely to have the wrong outcome to start with. So keeping that wrong outcome isn't so good. Whereas because of the structure of the problem, we're guaranteed to have the opposite outcome once Monty Hall opens up one door. So if we're more likely to have a goat than a car, and we're guaranteed to get the opposite one because of the structure of the problem, well, heck, we should switch. Okay, so that's a quick explanation. I could go into a lot more detail, but hopefully that helps a little bit. And we might revisit this when we get into probability too, because it's a really nice problem.